this goes. Well, vectors, the thing about vectors is it's different than normal numbers. When we're living in vector world, we're going to think about the old way of thinking about numbers as scalars. So for example, your age, or my age, whatever, your age is a scalar, right? Mine, 30. Dang, right? Ancient, jeez. But it's just a 30, right? It's just 30, it's just a number, that's all there is to it, right? You could have a length, like maybe 90 meters, right? Maybe I could put years on this 30. Again, we're kind of in that physics world where they love units on everything, so sure, we'll do it. We could have something like a temperature. Great, how about 72 degrees? That's your room temperature or whatever. So those are just kind of like the old school stuff. Now we're gonna get into vectors. And vectors, very importantly, they have a number, but they also have a direction. And so that will include things like force, and that will include things like velocity, speed plus speed with the distance, blah, 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 or speed with the direction. Now the ups and the downs, those are just randomly drawn arrows. But the thing about force and velocity is that force has that magnitude to it. You can hit something hard or you can hit something softly, but also it has a direction. You can hit something hard towards that wall, or you can hit something hard towards that wall. And so those things have direction on them. That means everything we're gonna do is gonna exist in 2 dimensions instead of 1 dimension. So that's more or less not all that important. It's just kind of getting us started, getting our brain thinking a little bit about how it works. What this is we're gonna do math with magnitude. Now magnitude is the word for like length, kind of, right? Magnitude, which is basically length. But more importantly, it's also going to have direction. How are we going to do this math? We're going to denote. How do we talk about vectors? We need 2 things, okay? We need to name them. If you name a vector, a lot of times they use the letter U, and they will put an arrow over top of that U, and that makes a lot of sense. It brings in the arrow from the ray, and the ray looks like a ray from geometry. Important to point out that a ray in geometry is different from a vector, because a ray in geometry, that arrow means it goes forever, and that is not the case with vectors. This vector has a magnitude that is finite. That's it. Even though it has the arrow on the end, that does not mean it goes forever. The reason it has the arrow on the end is because it tells us that we are going in this direction. It's starting at the beginning point here. This is like the start, and this is like the end. And that's what that arrow does for us, is it tells us where we begin and where we end. Now also, there's another way to do vector names, and that is with capital letters, with 2 capital letters. Now doing it with 2 capital letters is almost always better, okay? Because giving it 2 capital letters, it's gonna be the same looking ray, except for the first capital letter is the point where we originate, and the last capital letter, is the point where we end. And so this is just a little bit of a better way to name it because it's very clear about where we start and where we stop. Okay? So that's how you denote array. I could draw an array that looks like this. I could put C and D here. And how would I denote this array? I would just call it C, D with an arrow on top. Make sure it goes from C to D. C is the beginning, D is the end. But again, very easy so far. Now, as far as those little arrows go that are on top, sometimes they get lazy and they leave them off. If you're in physics, and I'm not really sure how IB does it, sometimes you have a teacher that is hardcore, the arrows are there or else. And sometimes you have a teacher who's not so serious about it. It's always a good habit to put the arrows on top. And so I do my best to always put the arrows on top, because why not, right? It's a better way to do it. If you see something on a paper where it's clearly talking about CD here, but they've kind of left the arrow off, that can be okay. Now, it's okay, especially when we have it in this format, because we know that the first one is always the start. So it's pretty obvious that the arrow is gonna go CD from C to D. So that's why the arrow, again, I like it because why not? Okay, we've talked about rays and vectors so far. They have magnitude and direction, okay? We've talked about how to talk about them and how to write them, but we haven't really talked about what is the magnitude. How do we talk about the direction? Well, we're not really gonna get to direction for a bit. Let's talk about magnitude first. This is kind of the first thing that we're gonna learn how to do with a vector. Magnitude. What is a similar word that means magnitude? You tell me, pop quiz. Length, right? How do we feel about that, physics kids? We feel like that's pretty much the same thing in physics? Magnitude, distance, length.
Length of the arrow, yeah.
Excellent, right? Length of the vector. I'm with you 100%. So, how do we find the magnitude? Well, if it's just in a vector AB, and it looks like this, from A to B, well, we're not gonna be expected to like get out a ruler and measure it in math class, okay? So most likely, they will just give you a number here. Maybe they will say 5. And they'll just list that as having a magnitude of 5. Now, how do we write that? Because we can't put AB is equal to 5, because that would mean that the vector is equal to 5, but a vector is made up of 2 parts, the magnitude and the direction. And so we need a little bit extra on this vector to symbolize that we're only talking about the magnitude. And the way we do that is with absolute value bars. So if you see those absolute value bars around a vector, that means it's talking only about the magnitude. So it could be in this format, or it could also be, you know, in this format of just a plain old letter U. Anything, if you see those absolute value bars, we're talking about the magnitude. Okay. Now, let's go back to our classwork here. We're given some information in the following diagram. OBCA is a square, 5, 5, 5, 5, while ACDE is a rectangle of length 10 and 5, okay? Let A equals OA. So this A can be basically thought of as this piece here from O to A. And then B is the vector from O, or the line from O to B. Okay, what we're trying to do now is determine if this is true or false. We're trying to compare these things. And the first one, they give you a nice little hint, is true. That A to C from A to C is equal to B. Now, two things have to be true. It has to have the same exact magnitude, the same exact length, and it has to have the same exact direction. Do these two things have the same exact magnitude and the same exact direction? Yes. That's why it's listed as true. So what do you guys think about the first one that they haven't given us? DE equals to B. Is DE the same thing as B? Anybody want to go for that? I see Grady shaking his head, no. Is DE the same thing as B? I know that this has a magnitude of 5. They tell us at the start that this rectangle also has a magnitude of 5. And so magnitude-wise, it is 5 and 5, that's great. But directionally, it is not so good. 5 is going up in that direction, and 5 is going down in that direction. And so, let me get rid of this stuff that I wrote on there. This would be false. Is ED equal to A? Well, ED is right here and A is at the bottom. Definitely not, right? No way. Those are not even close to being in the same direction. And again, kind of like I said in the intro before we started the video, this is weird, but it's definitely not hard, okay? It's definitely not a difficult process. BC equals A. True or false? True, with some guts. Is BC, the vector, equal to B, the vector? True. False. Nice, Grady. Some real guts on it. Way to go. Now this one, whoa, what are these crazy lines here? You tell me, what do these absolute value bars mean? Just the magnitude, which means we're not going to include the direction on this. We're only talking about the length or the magnitude. And so is only the length of BC equal to only the length of B? How long is BC? 5, because this is a square, they told us that. And how long is B? 5. And so is this true? Yes, this is true. Now here we're getting into multiplication. We haven't really talked about that too much, so we're gonna jump back to our notes just very briefly, even though I'm sure it's quite easy. Just so that we have some notes written down on this. And we're gonna go back to scalar multiplication. Right out of room. Scalar multiplication. So, this is a fancy type of multiplication, but it's also a very easy type of multiplication. We have to call it scalar because this is not a vector times a vector. If we tried to multiply a vector times a vector, that would be two things with distances and two things with directions. That would get a little complicated. This is scalar multiplication. Now, if you remember back to the start of the notes, a scalar number is just a kind of normal number, okay? It's just a plain old number like 30 or 70 or 100. And so a scalar multiplication is basically just a nice boring number multiplication. And because a scalar number, does that sound more like the length of something or the direction of something? Scalar definitely is more kind of in the same units as the magnitude, then it's going to affect the magnitude. So if we have, let's say that the magnitude of A is equal to 5, well, the magnitude of 3A is going to be 15. It is just 3 times more. It's affecting the magnitude there and it's changing it. But scalar multiplication does not affect with an A the direction. So again, so far we've done lots of stuff that only have to do with multiplication. We haven't really been doing any math that actually has to do with the direction of it. Now again, scalar multiplication. Okay, cool, vocab word. Okay, fine. Very, very easy to do, okay? Now, for these questions, we don't have those absolute value bars on those questions. And so what that means is that we still need to consider, I guess I need to keep the picture in. There we go. We still need to consider the direction. The direction is still important, but this 3, which is a scalar multiple, is not going to be changing our direction at all. So we still need to think about, could BD, which is from here to here, direction does matter, be the same as 3A from here to here. Now A right now is only this far. Before we even think about the magnitudes, are the directions lined up? Are we good to go? Yes. So we're good. Now, to kind of finish this thought, BD has a magnitude of 15, and 3A is going to have a magnitude of 15. And so this is going to be a true statement. So doing math with scalar multiples is really quite easy. Let's speed it up a little bit. CD equal to 2B. Well, let me erase this for a second. CD is going to be from here to here, and 2B is going to be from here to here doubled. Now, I know that up here is 10, and this is going to be double 5. Do we think true or false? False. This question is going to be false. I know that the scalar multiple only affects the magnitude, but for this question, we still need to be considering the direction. Okay, and the last question, CD is equal to 2A. I think this one is kind of obvious and almost waste of our time. We're moving on. Great, true. Okay, and like I said, our plan is going to be to kind of move down and just continue through this worksheet until we get something new, and then we'll just kind of stop. Now this says, express the following vectors in terms of A and B. Well, we have vector OC, and vector OC is this vector, and we want to express it in terms of A and B. We need to go back and take some notes. Again, it's not necessarily difficult at all, but it is a little different. So we're going to talk about vector addition. Now this is not scalar addition, this is vector addition, which means we're going to be including all of this stuff. This is where, so far it's probably been a little bit boring, and we're just learning our hellos and goodbyes in another language, and it's not that interesting. And here's where, again, it's going to stay pretty simple, but we probably could lose a person or two if you check out completely. Let's say that I have this vector, and we call this AB. Maybe we call it U. And I have this other vector. Yeah, this thing is driving me crazy with this pen. And we draw it like this, and we call this V. They really like U's and V's, even though they look so similar. So I like to put a little stand on my U. I think we've talked about this before. And I want to figure out what is U plus V. Well, in order to add these together, I want to think of it like a trip, like a journey, okay? So in order to add these together, I want to just kind of do what it says and follow my trip. Since these have directions, they're going to take me somewhere. And so, if I'm going to, let's see, why don't I do this? Take this one and clone it. And I'm going to have AB here, which is vector U. And then I can take this vector here, vector V, and I do it as a trip. That means once I finish U, I'm going to begin vector V, and I can put it like that and put them head to tail. Where B is the end of U, B is going to be the beginning of V. And then maybe I could kind of rewrite this a little bit, and let's get C as the end of V. So, in order to do this, this down here, our start against our end, we would call U plus V. Okay, it's almost like how, have you ever heard the phrase like, as the crow flies? Now that you guys are starting to drive around, you say, oh, it takes me, 10 miles to get to school, but as the crow flies, it's only 3 miles because I have to go way out and around the corners. Basically, going straight from the start to the end, that's where you get to the end. Now, this notation with the U's and the V's really kind of sucks at doing this because we just have to call it U plus V. There's really no better way to say it. But if we do this same question again, and we think about it instead as vector AB and vector BC, when we add these together, and this is our answer, start and end gives us the arrow, writing it with a head and tail notation, we can end up with AC as our answer. So again, this is probably the first place that we could lose somebody, and it's not a difficult process at all, but it is a different kind of thing. It is working different from addition than we're kind of used to. So if we kind of write this as a little equation, vector AB plus vector BC is equal to vector AC. This hopefully reminds you of a geometric property that you have to memorize in geometry, where if A equals B and B equals C, then A equals C. Anybody remember what that one is called? Starts with a T. Yeah, you rock. This is the transitive property, and it is not the transitive property, but it is very transitive-ish, okay? If you can find these links, like here, how the B and the B are right next to each other, those are almost like the subway stations where we can get from A to B and then from B to C. We can combine those together. So even if we're doing, like, let's say a really crazy, weird question, and we have AB plus BC plus CD plus DE, what would the answer of this monster vector algebra question be? AE, right? Nothing too crazy. The B and the B, transitive, we can just kind of say, okay, we went from A to C, and same with the C, and same with the D, and so we went all the way from A to E, and that's our new vector. Okay? Now looking at this triangle here, let's say we want to talk more about the magnitudes. Let's say that AB has a magnitude of 5, and the BC has a magnitude of 3. Well, it's not maybe drawn to scale, but let's say that this is 5 and this is 3. What is the magnitude of AC? Obviously, is it 8? Is it 8? This one's 5 and this one's 3. Can we just add their magnitudes and just make it work as 8? Not always. Maybe there's a very, very, very slight chance that it might work. But remember, this is a triangle, and we're being kind of inefficient as we go from A to C. We're wasting a lot of distance, traveling a little bit up and traveling a little bit down. And so the magnitude from A to C might be equal to 8, but will 99% of the time be less than 8, okay? There's only one possibility where AC would be equal to 8, and that would be if these two vectors had oh, I can't swing it up like that. Flip. The only time it would make 8 is if these two vectors were parallel and they were just perfectly making a straight line. 5 plus 3 makes 8. But 90% of the time, you can count on the addition of two vectors and thinking about their magnitudes to not be just add them up. So if that's the case, if this is a triangle and we're trying to figure out what the length should be on the bottom, then we need to use a different formula to find the measure of AC here. And if we have two sides of a triangle, if we're trying to find the third side of a triangle, we can kind of use the Pythagorean identity, the Pythagorean theorem, to figure it out. It's a little bit different, but pretty similar. Okay, let's go back. Now, let's express these terms. And again, we're going back to actually doing questions. I know it's a little, I feel like it's 100 degrees in here. I took off work this morning and super hot. So we need to go from O to C, and basically we get to make our own trip, okay? Who can make a trip that gets me from O to C? Well, we could go up, and then we could go to the right. And that is a totally legitimate trip that has taken us from O to C. Now, how do we talk about that? How can we write that? Well, we could write that as OB plus BC. And of course, we know that the transitive property, that's how we get from O to C. But this question says in terms of A and B, which means this is great. This is kind of in the spelled out heads and tails version, but we want to talk about just the kind of worse version where they have a smaller name like A and B. So OB is what we decided to do first. That is the B portion. And then BC, that is what we decided to do second. And BC is the same exact thing as A. And so down here in this box, we could put B plus A as our answer. Now this is a very easy question. Again, there's nothing crazy about this. If you were working ahead of me, maybe you put A plus B. Would A plus B be a legitimate way to solve this question? Could you do the A direction first and the B direction second? Of course you could. Of course you could. And so the rule of commutative, the rule of changing things around with addition is still there even in vector land. Okay, how about getting from O to D? Getting from O to D. We should be able to do this. It is a little bit more complicated than just A plus B. And I already heard one answer from Grady. I know that some of the physics fellas in the back are starting to snooze on me a little bit because we are going really slow. Anybody got the answer for vector OD? What do you got?
Is it 2A plus B?
Very, very close. Not quite 2A because we need to go.
Oh, 3A.
Excellent. Very good job. 3A plus B. There's another answer. B plus 3A, right? We can swap those around. And this at this point should be pretty quick. AD is going to be 2a plus b and ba get from b to a. Now here's where we're gonna get into our first kind of issue with this bottom box, getting from b to a. In order to get from b to a, we could go to the right. That would be an a. But now we need to go down. And if we go down, that's not B. We can't call that B because we've gone down, and B goes up. Now, because we're working with perfect opposites here, because B is going up and A is going, 180 degrees different, straight down, we can call that minus B. We're going down, it's like we're subtracting B. It's the opposite of B. Again, that's a pretty simple concept. If you need to go the opposite direction of something, you just put minus. And so, let's finish this off here. How can we get from A to B? Who's got the answer for that one? B minus A. Very good. Up, which is a regular B, and left, which is a minus A. How do we get from C to E? Again, this is all very repetitive. Layla, how are you feeling? Do you want to do one of these last three? You want to pick one? I would like you to do one of the last three. Do you want to do the last one and I'll come back to you in a second? Okay, so I'll be back to you in a second. Anybody else? I know Luke and Jackie, you guys look like you've seen this all before. Do you guys got vector CE, how we can get from C to E?
2a minus b.
Excellent. 2a minus b. Again, very repetitive. To get from B to E, this could be A, 3 A's, and then down minus B. That's not too bad. Like last night, I gave you a head start, and it didn't take us very long to get there.
Yeah, I can see that.
So we need to go from E to C. Let's start with the E here, Layla. Do we need to go up, down, left, or right first? Doesn't matter too much. We gotta go from E to C here. This is definitely not rocket science. So you're starting in this location. Are we going up or down? We need to go up. And so what letter do we use to represent up? It's either gonna be this one, which is a B, or this one, which is an A. Right, so we need to go up a B here. Excellent, so now we're up top, and now we need to travel left. Now, in order to travel left, well, B goes up and A goes right, so none of those work. But we can use opposites, like these minuses, to take us in the different direction. So, if we're using minuses, do you have the end of this question here? You know what it's gonna be? What do you got, Asia? You help her out? 2A, excellent. Because we need to go left A and left another A, that's minus 2A. Okay, we're done with the front, flip it over. And boom, we've never seen this before. So all of a sudden, we've switched it up that fast. All right, let's make it back to the nose, We saw some things that we have not seen before. What we have been doing, all of these first two columns, is very geometry. Okay? It's pictures, it's squares, it's shapes, it's ups, it's downs, it's lefts and rights. And there's a whole nother version, of course, is algebra. And so now we're gonna learn all the same things, but instead of hola, we're gonna be learning bonjour, you know what I'm saying? Dang, I can't believe I got so many laughs with that one. Come on. I'm just killing it today. All right. So, because we're doing algebra, what this means is that we're gonna put our vectors on a coordinate plane. Vectors on a coordinate plane. Now what that means, we're gonna have our x and y axis with the origin in the middle. And what we're gonna do is we're gonna call this O in the middle. That's the letter O. I don't really know how to make it out on a zero. That O stands for the origin, which again is not very difficult in case you see that. And so let's say that we have the vector and we have, A here. What we're gonna do is take this and we're gonna put it so that it starts at the origin. That means we could also write it as vector starting with O, because that's where its beginning is at the origin, and then some other letter. We can just, let's put a capital A. So we could put a capital A here. Now, because we're putting it onto the coordinate plane, now we're able to kind of measure it in the X and Y direction. This is a little bit different from geometry, where we were going like straight up, and we didn't really have to worry too much about the direction besides just thinking of it as left, right, up, down. Now we have these diagonal vectors. And so now we're gonna be thinking about them with their, that's not very good, with their X component and their Y component. That's gonna give us a third way to talk about these vectors. We could say that vector A is the same thing as vector from O to A using capital letters, using head to tail kind of setup. And we're going to say this would be equal to the X value and the Y value stacked on top of each other. It is not a fraction. There's no bar in the middle there. It's X on top of Y, and it's kind of like parentheses. Mine just look like this. It's kind of, some people like to put more of like the hooks on the bottom, but mine just start looking really ugly. So the best thing I do is I just try to do just nice little curves on there and deal with that. So our vectors are now going to be talked about using this X and Y, almost like coordinate notation. So if we're in X and Y notation, and let's say I'm just gonna pick these and say that this X component is 3 and this Y component is 4. So let's then put this as 3, 4. Okay, question 1. What is the magnitude of A? We want to figure out how long is that vector. I know that we have the numbers 3 and the number 4. The magnitude is 5. Do we just pick the next number that comes in order? No, we don't just pick the next number that comes in order. Where does the number 5 really come from, Smarty? Pythagorean theorem, right? This is a nice triangle with a length of 4 and a length of 3, and the magnitude would be Pythagorean theorem. So the magnitude is going to be the square root of x squared plus y squared. That's just the Pythagorean theorem. X squared plus y squared equals r squared. We square root both sides. And like he was saying, the answer is 5. Because 3 squared is 9, and 4 squared is 16, and 9 plus 16 is 25, and squared is 145. All right, magnitude, not too bad. Let's go back and let's see if we can solve some of these questions now that we've talked about this. Excellent, I think we can. What is the magnitude of A? Well, this is a 5, and a 12. And what's nice about algebraic is that it is not reliant on pictures. So don't feel like you have to draw the graph. I mean, you're welcome to, but the nice thing about algebra is that it's just numbers. And so the magnitude of A is square root 5 squared plus 12 squared. This is also a perfect Pythagorean triple, 5, 12. Does anybody know what the number is? 13. Because 5 squared is 25 and 12 squared is 144. And if you add them up, you get 169. And if you square root them, you get 13. Excellent. What about the magnitude of B? The magnitude of B is 1 squared plus 2 squared, which is going to be not perfect. Square root 5. That's just kind of how it's going to be. Up next, it's talking about the unit vector. Well, we've never heard of that. And we're actually going to save that just a little bit. We're going to come back to those unit vectors. Let's come down here. We've done this kind of stuff before. A plus B and A minus B and this 2A. What type of multiplication would you call this? 2 times A? Oh, you're torturing me now. Yes, this would be a scalar multiplication. Nice, nice, nice. Love that. And then, of course, it could get a little more complicated down there. And the whole idea is that this should not be as complicated when we are in algebra form. If it says A plus B, let's write down the A, 5, 12, and the B, which is 1, 2. It's 1, 2, right? It's not 2, 1. How do you think you add these up? You just add them up, right? Remember, these are the X metrics. The 5 is in the X direction and the 1 is in the X direction. And so if you put these together, how far did you go in the X direction? 6. And in the Y direction, what would the number be? 14. Again, I have to say it, this is new, but this is definitely not hard. Definitely not hard. A minus B. We could kind of write it like this even. 5 minus 1, 12 minus 2, 4 over 10. Now, it's not a fraction, so don't put the bar in the middle, which also means, no simplification, no reducing numbers. This is not a fraction. This is an X length and a Y length. How do you think we do a scalar multiple? You just multiply the numbers. Now, if it's a scalar multiple, and if I kind of write it how it looks, am I going to be multiplying the 5 times 2 or the 12 times 2 or both? Both, right. The 2 is just a scalar number. It does not have X components and Y. It is just a straight up 2. And so we're going to multiply both of these again, which is not like a fraction, how you do a fraction. This is not fraction stuff. 10, 24. Quite easy. What about A minus 2B? Okay, they're trying to make this longer, but it is still very easy. Minus 2B, which is 1, 2. Anybody got the X component? What do you got, Raina? You got it? 3. Genius. Anybody got the Y component? 12 minus 2 times 2? 8. Now this last question is asking us for the absolute value of A minus 2B, but it's not, remember, the absolute value has a new, what it means here. It is asking you for the magnitude of A minus 2B. Now, how can we work with the magnitude of A minus 2B? Well, the good news is we already know A minus 2B, right? These are the same thing. And so if we want to find the magnitude of this, we're going to do the Pythagorean theorem of this. So that would be the square root of 3 squared plus 8 squared. 3 squared is 9, 8 squared is 64. Add them together, you get 73 square rooted. And yeah, it's very, very likely that you're going to be getting numbers that stay in square roots. It's kind of weird when I stand so close to the camera like that. And here's where we get our most brainy question. No surprises, the last one on the page. What is a vector C that is parallel to A, but has a magnitude of 39? Does anybody know the answer? Because we're maybe already took this class before. Anybody know the answer to this last one? Or are we finally into new territory? What do you got?
1536.
Oh my God. Yeah, of course. Nice job. It is 1536. Now, why 1536? Well, this question says that it needs to be parallel with A. That basically means that we need to be thinking about A, which is 512. We need to be in the same direction as A, which is 512. We need to have a magnitude of 39. Now, we already know that the magnitude of A is 13. That was like the second or the very first question at the very top. And so if A has a magnitude of 13 and this new angle or this new vector has a magnitude of 39, we just need to be 3 times as big to turn our 13 into a 39. And so that's why we've basically done a scalar multiplication, making our vector 3 times as long, our magnitude 3 times as large, and that's how the smartest kid in the room over there figured out 15 over 36. What do you say? So you see how it says magnitude of 39? But we're talking about A. At the very top of this page, we talked about the magnitude of A itself. And the magnitude of A was 13. So how do you turn a 13 into a 39? It needs to be 3 times as big. 13 times 3 makes 39. So a little bit of a tricky question, but at the same time, we're just trying to think, how do we turn a 13 into a 39? It's just multiply. Okay. Now, let's look at the next page. We now are in 3 dimensions. Instead of an X and Y coordinate plane, now we have an X and a Y and a Z. And everything's gonna work pretty much the exact same, okay? Everything's gonna work pretty much the exact same. The magnitude of A is gonna be the square root of 2 squared plus 1 squared plus 2 squared. Just gonna do all 3 of those. 4 plus 1 plus 4 makes 9. Square root of 9 makes 3. The magnitude of B, 1 squared plus 1 squared plus 1 squared. 1 plus 1 plus 1 makes 3. Square root of 3, square root of 3. Again, unit vectors, Let's hold on to that. A plus B is 2, 1, 2 plus 1, 1, 1, which is gonna be 3, 2, 3. Again, maybe it's new, definitely not hard. A plus 2B, if we want to write it out in the long form, we've got a scalar multiplication of B, which is going to turn B into 2, 2, 2. So again, writing it out as long as I can for whatever reason, 2, 2, 2. Add these up straight across. The X components would be 4, the Y components would be 3, the Z components would be 4. 4, 3, 4. The magnitude of this new thing would be the square root of 4 squared plus 3 squared plus 4 squared, which is 16 plus 16, which makes 32, plus 9, which makes 41. Square root 41. Again, just very, very basic stuff. I know we're in the third dimension. And here we're back to a similar brainy style question. I know that Luke figured out last time. Does anybody have the idea for how to solve this last question on the bottom? We're talking about A, trying to get A to have a magnitude of 6. What is the original magnitude of A? 3. So we're gonna have to obviously double it. So we're gonna have to double whatever A is. We're looking for a scalar multiple of A times 2, boom, boom, 4, 2, 4. Easy, not too bad at all. I'm interested in how readable this is even gonna be. Okay, we've been just kind of chilling, but we've been skipping over unit vectors. I know. Tienes sueño. I mean, I got like 1,000 days on Duolingo and I can say a handful of things, so we'll get there. Let's talk about unit vectors. Unit vectors is keep the direction, but reduce the magnitude to 1. Think about the unit circle, right? The unit circle is the easiest circle. It's just a beautiful little circle with a radius of 1. And we're gonna do the same thing. We're gonna take our vector, we're gonna keep its direction, but we're just gonna reduce its magnitude to 1. Okay, well, how are we gonna do that? If we think about our vector that was 3 and 4, those numbers certainly need to become smaller, okay? They certainly need to be shrunken down. So we're gonna be using divide in order to bring those numbers down. Now, one thing we could do is we could divide them by 3, maybe divide them by 4, but the problem is if we shrink them at different rates, if we divide this one by 3 and we divide this one by 4, that's gonna change our direction, okay? That would shrink the x in a factor of 3, but it would shrink the y in a factor of 4. That would end up changing out our direction. That's not good. So we need to pick one number to divide both of these 3 and 4 by. We haven't talked about too many numbers in general. So what do you think we're gonna divide both of these by? 5, right? The only other number that we've really brought up, which is the magnitude. So in order to do a unit vector, you are just going to divide both by the magnitude. For this question, it would be 5 and 5. Now, the reason that this works, it's probably worth talking about because to me, this is one of those things that just seems like a math teacher made it up. But of course, it does work. If we think about this and we try to do the same formula on it again, that would be 9 over 25 plus 16 over 25. And so just like last time we got 9 plus 16, which makes 25, but this time we've almost put in the perfect counteract so that when we do 9 plus 16 and we get 25, there's already a 25 there. And so 25 and 25 just makes 1. The square root of 1 is just 1. And so that's how you make a unit vector, which means strange, but definitely not hard at all. Let's go back to the second page where we skipped over this, a unit vector of A, well, A is 5 and 12, and we need to divide those numbers by whatever the magnitude is. Now, I really hate sideways fractions, but this is one of those circumstances where you kind of get away with a little bit of a sideways fraction, right? Because there's really just not a whole lot of room to make them truly stacked fractions. So 5 over 13, 12 over 13. Unit vector corresponding to B, again, not very hard at all. 1, 2, divide, divide. This one is a square root 5 and a square root 5. So obviously we get to the question of rationalize it? I've been doing a lot of research on, I say a lot, I've been trying to make sure, again, keeping up with the vector stuff, and the 2 different resources I've used has not been rationalizing their denominators. They've just been leaving their unit vector as 1 over square root 5 and 2 over square root 5. Instead of making it square root 5 over 5, 2 square root 5 over 5, they've just been kind of leaving it how it is. Unit vectors of this form, they're not all that interesting. We're not going to do them that much, and so I honestly think the reality is probably just because it's not that important. We had some unit vectors on this where we had these 3-dimensional vectors, 2, 1, 2, divided by 3, divided by 3, divided by 3, 1, 1, 1, divided by square root 3, divided by square root 3, divided by square root 3. And yeah, you have to write small and it gets ugly kind of no matter what. Hopefully you have better handwriting than I do. You're just dividing it by that. Okay. It's 3:30. Oh God. We've been going at this forever. There's only one thing left. We're gonna do it. We're gonna do it. We're gonna power through. We're gonna be freaking vector rock stars at the end of this. All of this in one day. Okay. We're gonna head over here to dot product. Dot product, because they're going to use that little dot in the middle. So if they tell you, let's say that A is equal to 6 over 7 and that B is equal to 3 over, don't make it a fraction, 3, 2. Put my little vectors on my A's and B's just to be extra nice about it. The dot product is a strange thing, okay? When you first learn about it, it just seems super random. We'll talk more about what it is. I'm not gonna get into all of that too much today. But the dot product is a way to take both these vectors and kind of get a representation of them into one number. When we have them listed like this, the formula is not too bad. A times B, using dot product, it's not really the same thing as times, A dot B, is equal to XX plus YY. Now, X1 times X2 plus Y1 times Y2, right? If we want to be super good about it, we got to put those little 1s and 2s in there. But this is a really easy formula where you multiply the x's together and then you add multiplying the y's together. So for this exact equation here, it would be 6 times 3. That's the true meaning of multiplication. 6 times 3 makes 18. You would add that together, 7 times 2. You just do PEMDAS, so make sure you multiply these first, right? 18 plus 14, final answer, 32. Now here's the strangest thing about dot product is that the answer is 32, which is just 32, which is not a vector. It is not a magnitude and a direction. It is just literally 32, just a scalar number, just a flat 32 number. And that's just how it goes. Now this is a pretty easy formula. Let's go back and let's make this happen. So that would be down here in the bottom. A dot B would be 5, 12, dot 1, don't make it a fraction, dot 1, 2, which would be 5 times 1 plus 12 times 2, which would be 5 plus 24, which would be 29. Now, a squared, which is the same thing as like a dot A, would be 5, 12, 5, 12, which would be 5 times 5 plus 12 times 12, which would be 25 plus 144, which would be 169. And then of course b squared would be 1 times 1 plus 2 times 2, which would be 1 plus 4, which would be 5. Now if we look at the top, which is also asking us to do the dot product, well, we don't really know what those x and y values are. We can't use the same formula. We're not set up as nicely here. So, going back to dot product, this right here, this is the algebra formula, where we have those nice xy coordinates, even though they're not really coordinates, they're x on top of y to represent the vectors. But that is the algebra formula. And we're going to get a geometric formula as well. The geometric formula, if we just have a dot B, and we don't know what those values of A, what those X and Y dimensions of A, whatever are, it's going to be the magnitude of A the magnitude of B. These are going to be multiplied together in that traditional sense. And then lastly, cosine theta, right? Hey, we'll just bring trig into it and we'll just get there. And so, our geometric formula, not typically our favorite formula, because the algebra one is so easy, x times x plus y times y. X times x plus y, yeah, I'm glad I said that right. Then here we have the magnitude times the cosine. It can be a little annoying to find magnitude sometimes, and then the cosine. So let's think about this cosine here. Obviously, we're gonna get some kind of theta, and we're gonna put it in there. Let's think about kind of the range of things that we might get for cosine, okay? Cosine of theta. What are some that you have memorized? Think about the unit circle. The cosine of 0. Do you know what that is? 1. Excellent. What about the cosine of 30? You know what that is? square root 3 over 2. All right, so it's a unit circle, right? The cosine of 45 is square root 2 over 2. And the cosine of 60, here's a nice one, 1/2. What about the cosine of 90? 0. And then of course, 120, 135, right, blah, blah, blah. We kind of get all those. Once we pass 90, all of those numbers in the second quadrant, what do they all have in common? They're negative. And so sometimes our dot product will become negative when we're doing it geometrically. And of course, if we get all the way around to the cosine of 180, what's the cosine of 180? Negative 1. And of course, that kind of makes sense. If one vector is going this direction and the other vector is going 180 degrees in the other direction, they're 180 degrees apart and they have basically complete opposite directions, which is why you end up with negative 1. So, let's go back. Let's finish these questions. I can't believe the announcements have come on already. All right, A dot B in geometric would be the magnitude of A, the magnitude of B, and then the cosine of theta. The magnitude of A is 5. The magnitude of B is 5. And the cosine of theta. What is theta? How does A compare to B if we know that they are two different sides of a square? What would theta be? The corners of a square. 90, right angles. There it is. Okay. 5 times 5 is obviously 25. What is the cosine of 90? 0. And so, 0 is our dot product for A and B. We've learned something there. If two vectors are perpendicular, what is their dot product? 0. Okay, excellent. A squared is going to be the vector A, the vector A's magnitude, the cosine of theta. That's going to be 5 times 5. A and A. What is the theta difference between A and A? 0. They're the exact same, right? A's here and A's here, and it's just 0. Now, what is the cosine of 0? 1. So the answer here is going to be 25. B and B, they're both B's. The cosine is 0. What's the answer for the third one here? 25. That's the worst 5 ever. Here we go. There we go. Now, here we have some more complicated dot products. We're at the very end here. We're doing let's just do one of these questions. OE dot product with AC. OE is this one. Okay? What is the magnitude of OE? 15. It's not very hard. AC. AC is this one. What is the magnitude of AC? 5. That's not very hard. And the cosine of theta, what is the theta difference between one that's going to the side and one that's going straight up and down? 90. And what's the cosine of 90? 0. If two vectors are perpendicular, their dot product will be 0. And so there we go. All right, now let's go to the bottom. At the bottom here, it asks us for the cosine of angle theta between A and B. Any ideas? Obviously, we saw this other formula, which includes cosine a little bit in there, but that's our geometric formula. Here we're down in the algebraic world. Okay, we'll leave that for next time. What I've got is your homework. Now, on one hand, this homework is extremely important. Most of us are for the first time, or some of us at least, are for the first time learning about vectors, and we're certainly all doing math homework with vectors for the first time. And of course, it's going to have its own flair. This is different from physics homework with vectors, of course.